blue like powder shut up.
Okay, good morning everyone. A quick clarification on the homework. I think I forgot to mention that the problem with the bead on the upturned cone that has friction. Okay, so it's on a rough cone. So homework 2. The cone surface is rough. Kinetic friction will be a part of the problem. This is very similar to the problem that we solved in class where we had a bead on a cone, spinning cone, where there is also friction. Okay, rough cone. Yes.
Is it also fixed latitude, or can the ball move up and down on the
Oh,
cone?
it can move up and down. It can move absolutely. Yeah. It can travel along an arbitrary path. Like particle can travel. And any other clarifications that you require on the homework? For the spherical pendulum, is everybody okay with the type of way that you want to formulate the problem, the spherical polar coordinate system? Or do you want some clarification on that? I'll very briefly talk about the spherical polar coordinate frame. I think one of you asked me questions on that too. I think I'll help you set up the problem and then we'll go back to our formulation, Lagrangian formulation. So, I think if you have a typical spherical pendulum, right? Let's say this is the EZ, EX, and EY, and then I have the pivot sitting at some point O prime. This is some point O. Then I have the pendulum itself. The string of the pendulum. And I want to set up the spherical polar coordinate frame. And you asked me the question of homework too.
Thank you.
Thank you for pointing. So here is the situation. First thing is I'm going to drop a perpendicular onto the XY plane. Right, so here is the plane. And then I'm going to set up the unit vectors for the spherical polar coordinate frame. So this is a fixed point. So which means I can set up a unit vector along the length of the string of the pendulum. We call it as E suffix L. Then the second unit vector, please notice, is going to be perpendicular to the length of the string. Okay? So that's going to be the, if I call that angle as theta, it's going to be in the direction of increasing theta and perpendicular to the length of the string. Okay, so that's going to be perpendicular. And the third unit vector, if I call this as the angle phi, is going to be along the direction of increasing phi, and it is going to be perpendicular to this shaded plane that I have. Okay? So it's going to be perpendicular to this plane. So approximately this way, if I draw it out, this is E phi. Does this make sense to everybody? So EL and E theta, they form a plane. That plane is in some sense, if I draw a line here, if I plane that comprises of EL and E theta as the edges of the plane. If I swing back this plane, that will become one with this particular plane. Okay? Which means that the vector E phi is perpendicular to this shaded plane itself. Does this make sense to everybody? Yes, question.
So you're saying that those two planes are parallel, I guess?
They will become coincident. Right. So it's essentially like I have the palm of my hand here, and then I have another plane this way. So if I swing them back, they can become, it's almost like a hinge here, where they can collapse together, okay, if you let them do. Yeah? Which entails the fact that E phi is going to be perpendicular to the plane containing E theta and EL. Okay, and if you are looking at the unit vector EZ, that will have components only along E theta and EL. It will not have components along E phi. Okay? So, once again, E phi is defined on the XY plane. Okay, it's a line on the XY plane, which means that the direction EZ is essentially going to be perpendicular to E phi. Okay? Alright. Any other questions? And so if you have this as a setup, then essentially if I call this as, let's say, point P, then R of P slash O prime is the same as R of P slash O, no difference there. So this is going to be some length in the EL direction. You will not have the length as a fixed quantity. It's going to be a time varying parameter for you because it's a springy pendulum of some sort. And then if I look at the velocity, this is going to be with respect to, let's say, a fixed frame. This is frame F2. This is d by dt with respect to the frame F2 plus that's going to be there. Okay. Omega of the frame F2 with respect to F1. You will typically see fix one of the angles. Okay, so if I fix the angle theta, essentially I'm just going to have a conical pendulum which is going to be swinging about the z direction. Okay, so the increase of the angle phi, if I use a right hand rule, is going to take place about the EZ direction. So that's going to be phi dot EZ, that's one thing, which means that you have to take EZ and split it into components along E theta and EL. So there's a coordinate transformation that's important. Okay. Then I look at the part where the angle phi is fixed, and this essentially means that the pendulum is oscillating along this shaded plane, which tells you that it's the angle theta that's increasing in the E phi direction, increasing or decreasing. So theta dot in the E phi. And all you're going to do is perform the substitutions. If you need the acceleration, exactly the same idea. Once you calculate the velocity, just throw that into the mix here. So this is d by dt of 3p with respect to f2. So those are the three steps involved in every problem. Okay? So write the position vector, velocity, acceleration. The good news is that if you're doing the Lagrangian formulation, you can stop at the velocity. And that simplifies certain things, not necessarily everything. Yes?
So real quick, you have written the velocity of P in respect to frame 1 in the second arrow. Then in the third arrow, you have the velocity of point P with respect to frame 2. The frames change.
Oh yeah. Because, so essentially I'm just making use of this equation. So the most generic equation is that the rate of change of any vector with respect to a frame is the rate of change of that vector with respect to a moving frame or a rotating frame,
Okay, yeah.
and the angular velocity of that frame cross. Yeah. So that's why I write it as with respect to F2. So that is similar to writing this as.
I see, okay.
generic form. All right, and so that takes care of the spherical pendulum problem. I think you have two spherical pendulum problems, so you can use information from one to inform the other. You don't need to keep re-deriving stuff. The only difference for you is that this is going to be R of t or L of t rather than a fixed L. In our case, this ends up being 0 for a regular spherical pendulum. For a springy spherical pendulum, that's non-zero, and ends up making it a little more messy, but that's the cost of a degree of freedom. Okay. All right, and then the bead on the cone parallels whatever we have seen in the class problem, so I doubt if there will be many issues to tackle there. The other two problems are fairly interesting ones. I think problems 4 and 5. I don't have particular insights that I would like to offer, because if I do that, then that's essentially like solving the problem for you here. So go ahead and take a crack at those two. Once again, when you do the Lagrangian formulation, all of these will become slightly less dense, less intense in terms of the differentiation and so on. Okay? All right. Well, at least that's the hope. Okay, so I'm going to start from where we were last time. Okay? I'm going to start with Newton's laws. We will reach a very interesting point in this particular lecture as to the definition of the Lagrangian. It's a combination of kinetic and potential energies in ways that, if you're an engineer, it's a matter of convenience. If you're a physicist, it's a matter of principle. And it's something that perhaps deserves a more of a mental space to figure out why this combination works in the way it does. I will very briefly talk about it. We will not spend too much time on it, because my purpose is different. As an engineer, it's not going into quantum mechanics and Schrodinger's equation to use the Lagrangian there. Our purpose is to solve practical engineering problems using this as a tool. Okay? So for us, at least for me, the benefit of Lagrange's equation is that it comes from the Newtonian formulation. And it's a circular argument. If you believe Newton, you believe Lagrange. If you believe Lagrange, you believe Newton. So there is no question to answer here, really. So I start with Newton's formulation, and then we wrote it in the following form. Take summation I, Fi applied property of delta Ri. I look at a collection of I particles. I is equal to 1 to n particles. And summation 1 to n mi Ri double dot. Notice that del Ri is equal to 0. This is where we started off. I call this the first term is the term 1. This was term 2. I'm not going to go over the point of how we came across term 1 from last time directly. Term 1 ended up being summation j is equal to 1 to m, and we are assuming a holonomic system. Okay, holonomic. And the q pi's are generalized coordinates, so please keep that in mind. Term 1 ended up being 4. Summation I is equal to 1 to n. If I applied, the constraint forces vanished because we are using the principle of virtual work. Dotted with the Ri, the Qj, Lqj. Okay, this is what we ended up with term 1. And the thing inside that big bracket, I call it as the generalized force. It need not be a force, it could be a moment as well. Right? We'll see, we'll unpack the term very soon. So this I wrote down as summation j, qj, del h. at the second derivative term, okay? So I'm having the following summation to n mi Ra double prime, I write it as d by dt Ri dotted with del Ri, which we unpacked as the following. J d by I dqj del qj. This was the second term, okay? And then I did the following things. I sum over the I terms first, and then sum over the j terms without any loss of generality. That is fine for us. And mi is a constant for us for each particle. The mass is not a function of time. Okay, so rigid particles, and so we have the following. This is term 2 becomes summation over j first, big bracket, summation I, and the first term there, mi d by dt of Ri dot, I write it as d by dt of mi times Ri dot. Dotted with del R with del qj, and this is del. And in some ways, you can think of Lagrange's equations of motion as just the change of variables of Newton's laws. That's maybe a more simpler way of thinking about it. All right, and then we're going to do some manipulations. I'm going to write a generic formula here. So d by dt of A dotted, so two vectors A and B. I'm taking a dot product of these two. This is nothing but the product rule applied. So this is d by dt of A dotted with B plus A dotted with d by dt of B. And I'm going to compare what I have written on the left hand side of the panel with what I have here, and I'm going to call this term mi Ri dot as term A, vector A. I'm going to call this term as vector B. Okay, so I have, by comparison, vector A is mi Ri dot, vector B is here I will dqj. Can everybody here see my writing? Okay. So by doing this comparison, then I immediately recognize that I have d by dt of A dotted with the vector B, so I write the following. This tells me is d by dt of A dotted with B minus A dotted with d by dt of B. Replace everything instead of A and B, write it as mi Ri dot and all these things. So I have d by dt of A, which is mi Ri dot, dotted with del Ri del qj. Okay, this is equal to d by dt of mi Ri dot dotted with things are going to start taking shape very soon. You may recall from last time, we did something called as dot cancellation. I'm going to invoke that. Dri by dqj is the same as dri dot by dqj dot. So I'm going to invoke this dot cancellation into the first parenthesis on the right hand side of the equation. So rather than this, instead of rewriting those steps, I'm just going to say this is that. Okay? And with your permission, I'm going to do the following as well. Okay? Last term, d by dt of dri by dqj, the only term that will undergo differentiation with respect to time in this situation is this term in the numerator here, right? So this is actually going to be d by dqj of ri dot. I can do the shifting there. I can either do the time derivative first and then the polynomial derivative next. Okay, so this I'm going to replace as dri dot by dqj. Does this make sense to everybody? Okay. So then term 1 and term 2, I need to maybe write it all here. I'm going to copy term 2 and write it down here. Okay? So this is going to be term 2 after all those things have been done. Term 1, term 2. Summation over j. Don't forget there was a summation over I for all of these things. So everywhere I see there's going to be summation over I. So this is summation I 1 to n d by dt mi ri dot dri dot dqj dot minus summation I is equal to 1 to n, the last one, mi ri dot docketed dri dot by dqj del qj. So terms 1 and 2, save it there on the last panel. We're going to come back to it. And mind you, we are looking at particles, not done rigid bodies yet. But for a particle, we can define this quantity called as kinetic energy. It's a scalar quantity. It's half times mass times the velocity squared. Okay, we all know this. I'm not going to belabor the point. So kinetic energy of the ith particle in the system is going to be half times the mass of the ith particle, velocity of the ith particle square. Velocity square is nothing but a dot product between two vectors which are the same. So I'm going to write this as half mi ri dot docketed ri dot. This is the kinetic energy of the ith particle. We are looking at a system of particles, so I'm going to sum up all the kinetic energies and say, okay, the total kinetic energy of the system is the sum of all of these. So this is a net kinetic energy of the system. T is used for kinetic energy. Alright, so that's the first thing. Then here is what I'm going to do next. I'm going to take this kinetic energy and differentiate it with respect to Qj. Okay, so look at this. dt by dqj. What's that going to be? Summation I is equal to 1 to n. This is d by dqj, factor of a half, mi ri dot with ri dot and do it for this one particular step. The factor of half will vanish, as you will see soon. So this is going to be half mi does not undergo any differentiation because it's a constant, right? Half mi summation I, which is d by dqj of ri dot dotted with ri dot plus ri dot dotted with dri dot by dqj. All I'm doing is using the product rule. Okay, I have two terms here, ri dot and ri dot, and I'm taking the partial derivative of that with respect to the jth polynomial coordinate, the generalized coordinate. And because of the fact that dot product is commutative, a dot b is the same as b dot a. So this is essentially a dot b and b dot a. So they sum up together, the factor of 2 vanishes. Okay, so now I have d by qj is actually equal to summation I mi ri dot dotted with you see where that goes. The last part of that equation is that particular chunk that I have written there. So this guy is essentially dt by dqj. And likewise, I can do dt by dqj dot, I'll end up getting the following. Without going through the math, it is the exact same process. Instead of doing the derivative with respect to qj, I'm taking qj dot. I will end up with summation I. This is going to be mi ri dot dotted with dri dot by dqj dot, because my differentiation is with respect to qj dot. And you see that's here. Show that. This particular term, I can take the d by dt out and write the summation I first, without any loss of generality. So I can say that if I do d by dt, that's d by dt of that entire thing, and so I have this guy here as by dqj dot d by dt. It's almost there. Everybody with me so far? Last few steps and then we'll be on our way. So now I'm going to collect term 1 and term 2 and write them together. Okay, so term 1 is summation j qj del qj. Term 2 minus summation j d by dt of forget this has a q dot j, that's important, and this does not have a q dot, it's just q j. Del q j is a common factor, so I can rewrite it using the following way. So this is summation j. Look at this, I'm going to club together the qj term, excuse me, this is a negative and a negative, so that becomes a positive, so I'm going to combine them together, so this is qj plus dt by dqj minus d by dt of where T is kinetic energy of the system. Important, it's of the system, not of a single body. Okay? Now the trick that we have made use of is we are using a holonomic system. Okay? It's a similar process for a non-holonomic system, slightly more messier. You'll have to bring in the constraints, Papian form of the constraints and so on. So I did not want to take that route. But the great news is that this is a set of J independent equations, M independent equations. Each of the holonomic generalized coordinates are independent of each other, which means that if I am taking the product of this big quantity here, I should have put a different bracket. Okay, that's the whole big bracket. Because of the fact that each of my generalized coordinates are independent, I can say that the term within this bracket is the one that has to be equated to 0. Okay? So if I do that, and I'm going to write that down here, so since we have independent generalized coordinates, think of a double pendulum, theta 1 versus theta 2. The equation for theta 1, of course, there's a functional dependency on theta 2, but I can fix the presence of theta 1 and then I can obtain theta 2 independently. I can make the motion possible that way. Okay, so this implies that I have is equal to this. This is for the jth generalized coordinate. If you have a simple pendulum, you're going to write it once, because there's only one generalized coordinate, which is theta. If you have a double pendulum, you're going to write it 2 times, because j is equal to 1 and 2, theta 1 and theta 2. Okay. Alright, now this still doesn't look like the Lagrangian equations that some of you may know. So we have to do a few more things. First thing is qj. I'm going to split it into 2 things. One is called as a conservative generalized force, the other is called as a non-conservative generalized force. So this is qj nc and qj c. nc is a non-conservative generalized force, which means I need to define what is a conservative force. Non-conservative forces or dissipative forces. That's a more better way of arguing your point. So these are dissipative forces. Friction is a dissipative force. But I won't say non-conservative because I can have an applied force. That's not a dissipative force. I'm pushing the body with some force which is sinusoidal in nature. That's not dissipative. That is an applied force. But that's still not a conservative force for the following reasons. So what is a conservative force? It satisfies the following 2 properties. any force is a conservative force if the work done by the force, I'm looking at particles, okay? If the work done by the force on a particle between two positions is independent of the path taken by the particle to go from that position to the next. Okay, so let's say that I have position 1, position 2, and then a particle is traveling and it's going to take this particular path. If I have a conservative force performing work on that particle, this is F conservative, the net conservative force. So keep that in mind. There is a particle, position 1 to position 2. The work done by the force on the particle should be independent of the path taken by the particle. If the particle decides to go by a different path, then the net work done should be the same. That's the definition. First condition for a conservative force. Work done by a conservative force on a particle is path independent. The second condition is that if the particle travels along a closed loop path, goes from point 1 to point 2, and then travels back from point 2 to back to point 1, a closed loop path, the net work done by the conservative force, if I add up the work done on path 1 and then path 2, it has to end up being equal to 0. Okay, so the net work done by a conservative force on a particle that travels along a closed loop path is 0. Right? So write that condition here. Make it here. Net work done by a conservative force on particle along a closed loop path is 0. And of course, one can go into the details of conservative force fields and so on. I'm not going to do that. Yes, next question.
So what are some other non-conservative forces besides friction?
Well, as I said, an applied force is a non-conservative force. It does not satisfy any of these properties. If you have an applied torque, that's a non-conservative force. The only two conservative forces that we typically deal with in classical mechanics is one due to a central force field, gravitational force, and the other is, I guess, a spring force is also a central force. So typically only central force fields. But we categorize it as gravity and then springs. Okay, those are the only two things that we are going to be worried with, nothing else in conservative forces. So I want to briefly talk about the work done by the force of gravity on a particle. I know you've seen this in dynamics before. Perhaps it is boring to some of you, but I still want to do this. Okay? The work done by the force of gravity. Let's call it as F suffix g. Here is a particle. Point 1 to point 2. Particle is traveling from point 1 to point 2. Cartesian system. Let's say this is the unit vector I, unit vector j. So I'm first going to look at the infinitesimal work done. Okay, so I'm going to call this as an infinitesimal displacement vector from point 1 to point 2. So this is a dr. dr can be broken up into a component dx and dy. dx along the I-axis direction, dy along the j-hat direction. So dr is dx I-hat, dy j-hat. This is common sense, right? The force of gravity, if I write it using the Cartesian frame, minus mg, j-hat, and 0 I-hat. And we want to look at the work done by this force on the particle. So look at the words. This is the work done by the force of gravity on the particle. Okay? The infinitesimal work done. The scalar function. So F dot dr. And the net work done is a line integral from point 1 to point 2. So W12 is the following. So this is the net work done by the force of gravity on the particle. If I expand this is 0 I hat and g hat, after it dx I hat, dy j hat, dot product, and it gives me a scalar. 0 times dx is 0, minus mg times dy is minus mg. So W12, 12, the subscript implies that I'm going from point 1 to point 2. Okay. Let's say that this is a datum. Point 1 is at a height y1 from the datum. Point 2 is at a height y2 from the datum. Then this quite simply becomes the following. It's going to be minus mg times dy integral from y1 to y2. So this is minus mg dy. Okay. And so you can obviously see that no matter what the path I take to go from point 1 to point 2, I will end up having the same integral, which is why it is independent of the path taken. Okay, and if I reverse the path, then I'm going to get plus mg times integral from y1 to y2. If I add them up together, it's going to be ending up as 0, which is the second point I made there. So this ends up being the following. So this is minus mg y2 minus y. This I'm sure you've come across before. I'm going to leave this panel here, so this stays. Now, for reasons that depend on the person, you can either call it convenience or deeply philosophical, or maybe a little further, but these are all besides the point for us. I'm going to invoke a function called as the potential function. Okay? And we're going to define the potential function due to gravity as the following. Or what you know as potential energy due to gravity. So potential function due to gravity. I'm going to call it as Vg. Okay? This is defined as the work done by the particle against the conservative force as the particle goes from 1 to 2. Okay? So this is the work done by the particle, importantly, against the force of gravity, against the machinations of gravity, really, as it goes from position 1 to position 2. Does this make makes sense to everything. This is my definition. Okay, so, and if I look at the definition, this is W12, which is the work done by the force of gravity against the particle. That is the work done by the particle against the force of gravity, so one must be the negative of the other. Okay, so this implies Vg is minus W12, or you know this as mg times y2 minus y. This is actually from 1 to 2. Or Vg at any arbitrary point. If I assume that y1 is the datum, then I'm just going to have mg times y2 minus 0. Okay. Think of it that way. So in general, Vg is mgy likewise Vs is the potential function due to a spring. Okay, these are the only two things that we will be saying. So Vs is going to be defined as half a x square, okay, some x or y, some r square, I don't know. This is the potential function due to a spring. In problems where you don't have a spring, this fellow is 0. In problems where you don't have gravity, this fellow is 0. In problems where you don't have both, there are no conservative forces. Okay? And now we come to the punchline, is that if I take the derivative of Vg with respect to y and stick a negative sign to it, it is minus mg, which is essentially the force of gravity. Conservative force. And likewise, if I take Vs, which is the work done by the particle against the spring, and if I stick a negative sign to it by taking a differentiation, I get minus kx, which is the force exerted by the spring on the particle. Okay, and just for reference, you can think of it this way. Okay, this is the positive x direction. If I draw the free body diagram of the mass, this is static equilibrium position. The spring force is pointed in the negative x direction, so which is why I'm calling this minus kx as the spring force with a positive sign to it. I want to make this very clear. Okay? And I'm looking at the free body diagram. My positive x coordinate is defined to the right. My spring force is pointing to the left. If I define my positive x coordinate to be pointing to the left, depends on the displacement of the spring, but it does not really matter at all. This is completely convenience. The force of spring is always going to be opposite to the direction of motion of the particle. So that's minus kx or plus fs. Or in general, we can say the following. This is any set of conservative generalized forces can be written as the following. If you have gravity, you will have only one term. If you have spring, you will have one term. If you have gravity and spring, you will have two terms. This is just a generic potential function. A potential energy function, if you want to think of it that way. Okay, so this is the generic definition. I'm skipping through a lot of rigorous math here. It does not help our cause. Rather a crusade. Right, so now we are ready to write everything down. Most importantly, notice that your potential energy function is a function only of the coordinates and not the velocities. Okay, so this V is a function of only the generalized coordinates, not the velocities. And T is a function of all the velocities and not the positions. And so I can say the following. dV by dq dot is okay. Of course, this can also be functions of position depending on how one writes the velocity, so I shouldn't necessarily say that. This is also q1, q2, and so on. This is more general, okay? And once we have all of those things, now I'm going to go back to our final theorem and then start doing the substitution. And what people do typically, if you look at physics textbooks versus what we have done here is the following. We have taken this generalized force and we have broken up into two pieces. One that is completely independent of the velocities, which is given by the potential energy function or the potential function. Okay? But in many books, these terms are combined together and they will in general be called as velocity dependent potentials. I don't want to use the term because for us, there is a clear distinction between a conservative force and other non-conservative forces. So we want to split this and make sure that, okay, if I'm dealing with a conservative system, this creature is gone. If I'm dealing with a non-conservative system, both of them are there. Okay, so that's our distinction. Now I set up everything, put that back here. So d by dt, dt by dq dot does not hurt my case to say that this is also equal to the form, right? Does this make sense to everybody? dV by dq dot is anyway 0, so it does not matter if I stick it in there. This is equal to qj, which is the combination of those two, qj non-conservative, qj conservative, and this is the change of variables that I'm essentially talking about, is that the combination of t and v can be written together as the Lagrangian L so that dL by dqj is dt by dqj minus dv by dqj, dL by dqj dot likewise. So we can now write the generic equation. D by dt, dL by dq dot. This is equal to qj non-conservative, dL by dqj under the following caveats. This is for a holonomic system first. Means that all these qj's that I talk about are the generalized coordinates. kinetic energy, V is the potential energy function, and then L is the Lagrangian. And quite simply, the principle of minimum action or principle of least action that we will see very soon, in about a few weeks' time, says that the path taken by a particle is the one for which the integral of this quantity within the extent of the limits of the travel of the particle is a minimum. I hate to say the word minimum, it's stationary. It could either be a maximum or a minimum, but we are walking under the assumption that there is only one path for a particle. We are not looking at quantum theory. Okay, so for us there is only one single path for a particle as it goes from one point to the other. Out of a large number of potential paths, the particle is taking only one particular path. Okay? So that's the Lagrangian, this is the kinetic energy, this is the potential energy, and this Qj non-conservative requires some analysis. And here is the deal. Non-conservative forces come of two types. One is called as velocity independent non-conservative forces. Which I'm going to call as Fi, velocity independent, Vi, which means that an applied force, F naught times cosine omega t, that's a velocity independent force. And velocity dependent forces, which are drag forces, friction forces, these are the velocity dependent forces. Okay, so that's the second type. Which I'm going to call as F, I, and subscript V and D. They are to be treated separately in any problem. So, example of this is applied forces. Here, friction, drag. When I say friction, Coulomb friction, that's a function of velocity as well. Drag forces, linear drag, quadratic drag, all of these things. Okay. So Qj and C. If you recall, was written as the following: summation I, Fi applied, dotted it, dri by dqj. This is what we had written previously for Qj and C. This will now be split into two pieces: velocity dependent, velocity independent, and so I'll write it here. Qj and C is, if you are dealing with velocity independent forces, those forces are going to be independent of the velocity of the problem, okay? Which means that they will not be functions of Qj dots. So you will just write them as the following: Fi, velocity independent, no change. But it is possible some forces might also be velocity dependent, so I would have to add the contributions of those creatures. And since those forces are functions of velocity, I am just going to use the dot cancellation idea and say the following. We will not rigorously derive this as well. I'm using the dot cancellation idea here. So dri by dqj for a velocity independent force becomes dri dot by dqj dot, and all of this we will work out examples where you see how these end up. And the big question is, okay, what if I have a rigid body and apply a torque? How do I account for that? I'm going to sneak in one more term. Once again, without much ado, mi, which is the applied torque or the applied moment, okay, dotted with d omega I by dqj dot. This is quite silly because all of this information is actually packed into the velocity dependent formulation, essentially by saying that dri dot is some distance times d omega. And I'm just taking the Ri, copying it to the force. The dot product of force and displacement becomes a moment. Okay, I'm sorry, a product of force and displacement. In this case becomes the moment m, and then I'm left with the angular velocity of the ith body. Angular velocity is a property of the rigid body. It's not a point property. Position vectors are point properties. Moment is applied on the entire body. It's not applied at a point. Okay? So these are the three things that we will typically have. And this is all for just a holonomic system. And with the next 15 minutes, I just want to quickly sketch out something. So in some senses, let's say that there are no non-conservative forces acting on the particle. Perhaps an example might be better. Let me just take a simple picture. Gravity, so length L, point O, this is point P. Let's say that there is a constant force acting on this body. So that force is F is F naught cosine omega t. The force is such that it's acting always perpendicular to the length of the just for simplicity as the pendulum travels along. Obtain the equation of motion. To obtain the equation of motion, the initial steps are all the same. Okay, you have to set up a coordinate frame. Typically, you can set up a polar coordinate frame, dr, e theta. You always have to obtain the velocity with respect to an inertial observer. That does not change. Okay, you cannot do this with respect to a moving observer or a rotating frame. I can use the unit vectors of a rotating frame, but as long as I'm depicting it with respect to a stationary observer, that's good enough. So position P/O is L E R. I need only the velocity, so V P/O is going to be L E R dot, okay, to do the derivative, or this is just L theta dot. E theta is going to be tangent to the path. That is trivial, right? Does this make sense to everybody? Okay. Then I write the magnitude of the velocity, which means that my kinetic energy is obtained as half m Vp square, which is half m L square theta dot square. To obtain the potential energy, you can choose a datum. A datum is a fixed line, does not change with the problem. You can choose any datum. Okay. Let's say that I choose the top horizontal line as a datum. Let's say I also have one more datum here. This is the undisturbed position of the particle. So I'm going to choose two datums just to show you that they end up being the same. So it's a common confusion that I've seen before. We will solve more complicated problems, just bear with me. So if I choose datum 1, potential energy, in terms of the generalized coordinate, I should mention this is a holonomic system, theta is the generalized coordinate. I'm taking a lot of liberties here. So V with respect to position 1 is going to be, since you're looking below the datum, this is going to be the following value. So this is theta, and this is L cosine theta. So minus L cosine theta times mg. Mg times y is the potential energy function. So this is minus mg L cosine theta because I'm looking below the datum. If I choose the second line as my datum, what's my potential energy? It has to be mg times the distance of the particle at any point in time from the datum, which is going to be the total length L minus L cosine theta. So that's going to be this little distance there. Does that make sense to everybody? In the first datum, my distance is from the point here all the way to where the particle is sitting. So I just drew that out there. That's my vertical distance, sorry. Second one, the vertical distance is from this datum all the way to where the particle is sitting. It's a positive distance. Mg times L minus L cosine theta. So these are the nuts and bolts of the problem. Write your potential energy first, write your kinetic energy next. Before that, get your velocity. But much before that, decide whether the system is holonomic or not. And once you decide it's holonomic, after going through the Pfaffian tests, decide on a generalized coordinate. We've done all that hard work before, so I'm just taking some liberties. Then I start calculating the following. Lagrangian is T minus V. So in the first instance, it's going to be T minus V1. So that's going to be half m L square theta dot square plus mgl cosine theta using the potential energy function V1. Then L2 T minus V2, which is going to be half m L square theta dot square minus mg times L minus L cosine theta, which I'm going to write as minus mgl plus mgl cosine theta. I want to make sure everybody is on the same page. Any questions so far? Okay. And the reason why I'm using two different datum is that essentially it makes no difference to my life. Today you come and choose the first line as your datum, tomorrow you come and choose the second line. If I take the derivative of the Lagrangian with respect to the generalized coordinate and the velocity, the generalized velocity, I get the following. dl by d theta, partial derivative, so you are taking only the terms that contain theta and then differentiating them. You are not differentiating the terms that contain theta dot. Please. Once again, I've seen some common issues with that. In the first case, it's this term that I'm differentiating. In the second case, it is this term that I'm differentiating. In both the cases, it is the same damn thing. This creature minus mgl does not play a role in my calculations, which tells me I can choose anything as my datum. I can choose a line in the middle of the problem as my datum. I will still end up getting the same result. Okay? So, if I do the differentiation, in both cases, I'm just going to call it as dl by d theta is minus mgl sine theta and then dl by d theta dot. It also end up being the same for both because I'm doing partial derivatives with respect to theta dot only. I'm not doing the chain rule here. I'm not taking the time derivative. That will come later. So only one term contains theta dot. One term only contains theta dot. The rest of them don't undergo any differentiation. And so I'm going to have ml square theta dot. Then the non-conservative force. So far so good, right? Everybody on the same page? Okay. Non-conservative force, how many J's do I have? I have only one. How many I? I have only one particle, so J is equal to 1. I is equal to 1. Alright. And so I'm just going to call it as Q non-conservative. This is going to be F, and in this case this is a velocity independent force, so FVI dotted with dr and dq, but instead of dq I'm going to call it as d theta, right? So in this case this is going to be the position vector by d theta. So wherever the force is acting, you're going to take the position vector of that point where the force is acting, because we're going to do rigid bodies as well. Forces can act at points. So this first creature you see here is the position vector from a stationary observer